equilibrium occurs when you have opposing reactions that are occurring at equal rates. It doesn't mean that you have equal amounts of the reactants and products. It just means that the reaction is going in the forward direction as fast as it's going in the backward direction. So actually at equilibrium, your concentrations are pretty set. So in this case, I've used colors so we can kind of eyeball it and see where we are. It looks like the blue and the gray are more favorable than the pink. So in other words, this is at equilibrium and products are favored over reactants. And we can describe that relationship of products to reactants as an equilibrium constant. So Kc, that's an equilibrium constant based on concentration for the C. It's basically products over reactants. And so for this one, I would expect the number to be greater than 1. But more specifically, we use the concentrations. The brackets just mean molarity. I would normally raise these to a power, but the exponent that I use is the coefficient, and these are all coefficients of 1, so I don't show that. Okay, and so this equilibrium constant expression, again, it's just a way of saying where the equilibrium is, which is the concentrations that are most stable. And apparently for this system, it is most stable with more of the blue or more of the product. And in fact, I don't have concentrations, but I could just count dots in this situation. Under these conditions, and so that's something that you should know, is that what is most stable can vary with temperature, but it is not changed by changing concentrations or adding a catalyst or anything. If I did something to change the situation, once it's at equilibrium, if I added some gray, it's going to make this concentration of gray or product be too high. And so the reaction will occur until we get back to this ratio of 8. So in that situation where you add some reactant or product, you could kind of assess how far you are away from that magic ratio, the equilibrium constant, the ratio of products to reactants, and then decide what's going to happen in order to get back to that most stable ratio. So in other words, in this one, I'm adding some of the gray. And when I do, what's going to happen is that I'm going to now have too much product. I'm going to calculate what's called a QC, and the QC is not the same thing as the KC. It looks the same, but you can kind of think of these as initial concentrations, not equilibrium concentrations. So if I put in the numbers, then I can kind of assess where I am. And the way that I have done this with extra gray, when I calculate this ratio, it'll come out too high. And by too high, I mean that my QC, calculated with these initial concentrations, will be bigger than that 8 that I had before. It'll be bigger than my KC. So again, this reaction quotient, QC, it's just a way to basically you put the numbers in and see how it comes out compared to the known equilibrium constant. On this one, if I put in the gray, it would come out too high. Too high means I have too many products or too much product. And so that means that to get rid of that extra product, it needs to react this way to get rid of that product. So if I add gray, the reaction will shift to the left, away from the product. Now I could calculate a QC for this situation here. if I was doing this one, when I calculated my QC, I would just put in the concentrations and I would get 8. And so when these are equal, that's when you're at equilibrium. Again, the QC is just a way to see where you are relative to equilibrium. Red and my product is yellow. When I mix them together, I get an orange mixture, which means that I have kind of a mix of red and yellow, maybe kind of equally. So let's make some predictions. What if I add some A? And so if I add A, Le Chatelier's principle says that the equilibrium will shift to get rid of that A. And how does it get rid of A? It reacts to the right. And so I would expect the reaction to shift to the right. Now let's think about QC. Remember that QC is basically products over reactants. And so when I add A, it's a reactant, it's going to make QC get too small. So if I increase this part, it's going to make QC get too small. And so it'll react to make more product, which will help the QC get larger. So remember, QC is our way to decide how far or which direction we have to go to get to equilibrium. So if we add A, QC decreases because A is on the bottom, and so the equilibrium will shift to the right. If I add C, equilibrium will shift away from that, so that part, what will adding C do to this? Well, C is a product, and so it will make QC go up, and the reaction will shift to the right to get rid of that extra product, or to the left to get rid of that extra product. Last one, if I remove A, so in other words, if I do like another side reaction or something to take that away, if I'm taking away reactant, well, reactant's on the bottom, so if that number gets smaller, it's going to make my QC get too large, so it'll increase my QC, my reaction quotient, and equilibrium will shift to the left to replace that. And so notice the pattern that I have, that when QC goes too high, it shifts to the left, and when it gets too small, it shifts to the right. If you just remember that QC is products over reactants, that makes sense. Okay, I want you to note changing these concentration change the reaction quotient they do not change the equilibrium constant Kc. We said earlier that Kc, the equilibrium constant, can change with temperature. It does not change when you change concentrations. It doesn't change with the catalyst. It doesn't change with changing pressures if you're dealing with a gas, but it can change with temperature, and it will, depending on if the reaction is endothermic or exothermic. So how we analyze this is we look at our change in enthalpy here and decide if the energy is a reactant or a product. In other words, this reaction, this is a negative enthalpy change, so this is exothermic. If it's exothermic, you can think of energy as being a product. And if energy is a product, well, we can make predictions. If I warm this, it's just like any other product. If I add a product, it's going to react to get rid of that product. So if I warm it, it will shift this way in order to get more reactants at equilibrium. Well, more reactants at equilibrium, what would that do to Kc? If I have more reactants at equilibrium, that's going to make this number smaller or decrease. Again, the trick to making these predictions is to treat energy as a reactant or product, and then you can think of it just like you did with concentration. If you give it more energy, it reacts to get rid of that energy. Let's look at this example. We can decide if a reaction is endothermic or exothermic based on what happens when you warm it. Let's just say that I'm starting off with kind of this light blue. I have colorless reactants and my product is dark blue, so it's kind of light, so it's somewhere in the middle. And then I warm the reaction, and what happens is that it gets really dark blue. So to figure out if this is endothermic or exothermic, let's think about which way it shifted. So when I warmed it, it shifted to the right, okay, to make more blue. So that means that, warming, it means I'm adding energy. And so that means that energy must be a reactant. And that would be true if the reaction was endothermic. In other words, my change in enthalpy here must be a positive number.